In section 1.5, we're going to learn about linear first order differential equations. So we have already learned about separable differential equations in section 1.4. We're adding one more type of differential equations to our arsenal of DEs that we can solve. So first, let's just define what it means to be a linear first order DE. That is a differential equation that can be written of this format as listed here. One thing that I want to emphasize is there is a 1 in front of the dy dx term. So that's important in order to be able to call it in standard form. So you'll notice what we have here. We have a dy dx and we have a y. Notice that those two terms that I drew arrows to are linear in a sense of they're not being squared, they're not being square rooted, there's not a natural log attached to it. Those are just truly y and y prime, or y and dy dx. And then we have these other two functions in terms of x, which are denoted p of x and q of x. We're just going to assume that those two functions are continuous on an interval. So as long as we have that set up there, then that means that we'll be working with a linear first order differential equation. So we have a particular method that we want to use in order to solve these differential equations. And it's really quite slick what we're doing. What we want to do, if we look back up at this upper equation, I'm kind of boxing in here the left-hand side. We would like to multiply by something that we're going to call an integrating factor so that the left-hand side can be realized as the derivative via a product rule. So if you think back to the product rule, and I'll write it up in the margin, the product rule says that if we take the derivative of a product of two functions, which I'll call f of x and g of x, then it outputs f prime of x, g of x, plus f of x, g prime of x. So in particular, if we will let one of those be y, where y is assumed to be a function of x, then the product rule would output dy dx times f of x plus y times f prime of x. All right, and so we're seeing the dy dx and the y. What we need is for this p of x and whatever else is out in front to be related by way of a derivative. And so we're going to say, okay, well, whatever this thing is right here, we want its derivative to be that same thing times popping out something in front. And so we're going to use the exponential to get there. So let's take a look down here at the methods for solving these linear DEs. We're going to calculate this integrating factor. This is going to be kind of this magical function that we're going to multiply by to rig up the left-hand side so that it becomes the derivative of a product of two functions. And how we're going to do that is we're going to first call it rho of x. I want to note that that's the Greek letter rho, which is not lowercase p. So please draw that appropriately when you're working out problems. Rho of x is going to be defined to be the natural exponential function, and up in the exponent, we have the integral of p of x dx. So we're doing this again very carefully so that when we multiply through by this integrating factor, we see that product rule occurring. Once we find our integrating factor rho of x, we're going to multiply both sides of the equation by that. So that way we're not changing the integrity of the equation. And then what we're going to do is we're going to recognize that the left-hand side of the resulting equation is the derivative of a product. Now, this is a super important step. What I see students do a lot is just take it for granted and assume that that left-hand side is the derivative of a product without checking it. Now, it's easy to make mistakes here. And probably the most common mistake is, let me clean up here. If we actually go all the way back up to this original equation, what I want to emphasize here is the sign in front of p of x. So in this case, the plus gets carried down into this integral. So if that happens to be a negative x squared there, then you have to plug in negative x squared in here. If you drop that negative sign, then this whole thing falls apart. So what I'm getting at here is when you're doing step 3, check the product rule. Run through and take 30 seconds to make sure that what you have on the left-hand side is in fact the derivative of a product of two functions before you proceed with this. Now, once you've recognized that it's the derivative of a product, you essentially want to do the reverse product rule. You want to rewrite it as the derivative of that product. And assuming that you did everything correctly and assuming that it was a linear DE to begin with, that product will always be the integrating factor times Y. Always, always. And then, of course, whatever's left over here on the right-hand side. Now, the beauty of this was we started out with a differential equation that had x's and y's intermixed. Now, what we have done is we've recognized the left-hand side as the derivative of a product. And as important is the fact that the right-hand side is entirely in terms of x. So what that means is we can use the fundamental theorem of calculus part 2, which says if we integrate a derivative that cancels out, and if we integrate the left-hand side, we had better integrate the right-hand side. So the integral and the derivative cancel out here, leaving you with the product of rho of x, y of x, and then just carry out this integral as usual. And then typically we solve explicitly for y. So I just state here in number 4 that we want to solve for y to obtain the general solution. Now remember, what I mean by general solution is that that solution is going to be in terms of x. If you're given an initial condition, then you can also solve for c. So we're going to jump right in here to our first example and just really see how we can solve these linear equations and how the integrating factor is calculated and also used to solve these. So first of all, check that this is a linear DE. So we have a linear derivative and a linear y term. And we have continuous functions here throughout. So I'm just going to make a note here that yes, indeed, this is a linear differential equation. Now let's calculate our integrating factor rho of x. So here again is where you need to be very careful. Make sure you include that negative sign in when you're calculating your integrating factor. So it's e to the integral of negative 2x dx. And so when I integrate negative 2x, I get an e to the negative x squared. Now, one thing that I failed to mention up above when we were talking about step 1, normally when I'm taking an indefinite integral, I'm very careful about writing my plus c, and it's more important than ever in this course in particular. However, this process for solving linear first order DEs will work for any integrating factor for any plus c that you use. So I'm always just going to assume c is 0 here, since that will suffice to solve the system. But when I go through step 4, I need to make sure to write my plus c. So here's my integrating factor. I am now going to take a look at the original DE and multiply both sides through by this integrating factor. So I have e to the negative x squared y prime minus a 2x e to the negative x squared y equals e to the negative x squared times e to the x squared. Now, according to our exponent rules, x to the a times x to the b is x to the a plus b. So using that, I get e to the 0 or just 1. So now what I'm going to do is I'm going to look at this left-hand side and I'm going to check to make sure that that is the derivative of a product. So let's see here. According to our process, this should be the derivative of y times the integrating factor e to the negative x squared. So let's go ahead and check. Let's run through the product rule. The product rule would give me dy dx times e to the negative x squared plus y times, I have to use the chain rule here, I'm going to kick out a negative 2x e to the negative x squared. And so now compare, and sure enough, that is equal to what I had highlighted up above here in orange. So I have done essentially the reverse product rule here. And all of this is still equal to 1, which was what our right-hand side was. So now I look here at this derivative and I say, how do I undo the derivative? Well, I just apply the integral with respect to that same variable. So I'm going to integrate both sides. On the left-hand side, my integral cancels my derivative. So I'm left with y of x times e to the negative x squared. On the right, the integral of 1 is x plus c. And then to finish this off, I'm just going to solve explicitly for y of x. So you can either think of it as dividing by e to the negative x squared or multiplying by e to the positive x squared, however you'd like to think about it. And so y of x equals e to the x squared times x plus c. All right, and this is our solution of this first order differential equation. Now, remember, if you're working a quiz or an exam, the beautiful thing about differential equations is you can always check your answer by plugging it back into this original DE that I just highlighted in green. So if you have extra time on a quiz or an exam, run through and plug in y and its derivative and make sure that that is satisfied. Since we were not given an initial condition, we can stop here with this general solution. No need to solve for C. All right, let's take a look at 14. Again, let's double check that this is a linear first order DE. First order, yes, we have a y prime and we have a y, and those are both linear and first order. First order because the highest derivative is the first derivative, linear because they're both raised to the first power. However, this is not in standard form. So we cannot begin to find our integrating factor until we get that coefficient in front of our y prime term to just be 1. So I'm going to take this entire equation and I'm going to divide through by an x. That's going to leave me with y prime minus 3 over x y equals x squared. And so at this point, I'm going to recognize that this is standard form and this is linear. And we can move forward with calculating our integrating factor rho of x. So that's always e to the integral of, here again, we want to include the symbol or the sign in front, minus 3 over x dx. And now let's go ahead and integrate. That is an e to the negative 3 natural log of x. And using logarithm rules, that's e to the natural log of x to the negative third. And then canceling out, this whole thing reduces to x to the negative third power. So now what I'm going to do is I'm going to refer back to my simplified DE or my DE in standard form, and I'm going to multiply through by this integrating factor. So I have x to the negative 3 y prime minus 3x to the negative 4. If I bring that additional x on the denominator up, times y equals x to the negative 1. All right, so here's where I like to check. We should have that the derivative of our integrating factor, x to the negative 3, times y, that should be equal to what I have just highlighted in orange. So let's just take that 30 seconds and double check to make sure that that is true. So if I follow through with the product rule, I get a negative 3x to the fourth y plus x to the negative third y prime. And sure enough, that does equal what I have up here in orange. And this equals an x to the negative 1. Or if you would like, a 1 over x. So here's where we're going to bring in that fundamental theorem of calculus. We're going to integrate both sides with respect to x. That is going to cancel out the derivative on the left. So I have x to the negative third y, or y of x, equals the natural log of the absolute value of x plus c. And then finally here, I'm going to multiply by x cubed on both sides. And I conclude my general solution is y of x equals x cubed times the natural log of the absolute value of x plus c. All right. So we've seen a couple of examples of how to go through the process of solving linear first order DEs. I'd like to remind you guys about the theorem of existence and uniqueness that we talked about several sections ago. And relating back to that, it says if the functions p of x and q of x are continuous on the open interval I containing the point x naught, then the initial value problem as stated here, so we have our linear first order DE and an initial condition given, has a unique solution y of x on I. So this is just an immediate consequence of the theorem on existence and uniqueness of solutions, specifically for this type. So we always have not only guarantee existence, but also guaranteed uniqueness of solutions. So as a result of this theorem, we know that these types of DEs, that is linear first order DEs, they never have singular solutions. So we spoke about singular solutions in the previous section. Those are those sneaky little buggers that arise from values that cannot come from choosing a particular C value in a general solution. We don't have to worry about those in this section. As is customary, we'd like to end by talking about some applications of these differential equations. So in the previous section, when we talked about separable DEs, we talked about the natural exponential growth and decay function. We also talked about Newton's law of cooling. In this section for linear DEs, we're going to talk about mixture problems. Those are pretty standard as an application. And so we have quite a large setup here. So all of this is going to be setting up for our mixture problems. So what we have is, suppose we have a tank containing a mixture of solute and solvent with a specified constant inflow and outflow rate. So we have several things here, solute and solvent, and we have a constant inflow and outflow rate. We may use a linear differential equation to model the amount x of t of solute in the tank at any time. So I just want to highlight what x of t is representing because I think very often students forget what that is. So it's the amount of solute. So maybe you're trying to dissolve sugar or salt in water, or maybe you're trying to dilute some pollution, something of that nature. We're measuring the amount, whether it be in grams or ounces or liters or whatever it may be. All right, so then here's a list of all of our variables. V of t is going to be the volume of the solution at a time t within the tank. Notice that this is dependent on our independent variable t. We have the constant inflow rate of the solution, again, constant, so independent of t. We also have the constant outflow rate, which is R sub O, so Ri and Ro. We also have the constant concentration of the solute per volume of the inflow solution. All right, so that's whatever's being brought in. Are you bringing pure water in? Are you bringing some kind of a brine in? What is it? That should be some constant concentration that you're adding. But what is changing with time is the concentration of the solute of the outflow solution. So you're mixing some solution in with what you started. And so as more and more gets mixed in, that concentration is changing with time. So I just want to emphasize here that the volume may or may not be changing with time, and the concentration of the solute is definitely changing with time. So there is a special case where the volume is constant. The volume is constant if and only if the inflow rate equals the outflow rate. So you're adding as much volume in as you're taking out in a given unit of time, and so then your volume is at a standstill. Otherwise, your volume will be changing with time. We can express the concentration of the outflow solution, C subscript O of T, as the amount of solute, X of T, divided by volume. So concentration, again, is just going to be amount per volume here. So here's where we're seeing that X of T value that we're going to be solving for. So putting it all together, we can model this rate of change in the following way. The amount of solute is changing with respect to time by taking the rate of the inflow times the concentration of the inflow minus the rate of the outflow times the concentration of the outflow. And you'll notice here that this equation is just plugged in right here. Now you'll notice that they separated the x outside. That's because this differential equation has the dependent variable x. So we want to think of this as a linear first order dE. Here is the linear x prime and the linear x value. Now, on quizzes and exams, I am not going to assume you have this memorized. I will provide you with this differential equation. You will just need to know what all of those variables are representing. So we have one example here to illustrate the mixture problems. And you'll notice that I provided an entire page for you guys to work this problem out. Do be aware of your white space because you'll need every little bit of it. So what I'm going to do actually to conserve some white space is up above in the top margin, I'm going to write out all of the given information. So we have, first of all, number 36 from the textbook. A tank initially contains 60 gallons of pure water. So we know that our initial volume is 60 gallons. And there's also one little bit of information that oftentimes gets looked over. Pure water. They're telling us that the gallon initially has 0 solute. It is pure water. So that means at time 0, there is 0 amount of solute. So I'll say 0 pounds, write it like lbs. 0 pounds of solute in that initial tank. Okay, so we have brine containing 1 pound of salt per gallon enters the tank at 2 gallons per minute. So this is all of our inflow information. So we have the concentration of the inflow, C sub I, is 1 pound per gallon. And we know that the rate at which it's entering the tank, R sub I, is 2 gallons per minute. It says, and the perfectly mixed solution leaves the tank at 3 gallons per minute. So our outflow rate is 3 gallons per minute. And so what we notice here before I even read on is that our outflow surpasses our inflow. So our volume is decreasing. We're losing more of our mixture than we're gaining at a time. So then they made a statement, thus the gallon is empty after exactly 1 hour. Part A, find the amount of salt in the tank after T minutes. So in other words, we can write this mathematically as find X of T. So solve the differential equation. And then part B, what is the maximum amount of salt ever in the tank? So I want to find X max. I'll write it as. Okay, so here's our setup. What I'd like to do first is just figure out how I'm going to express the volume in terms of time, V of T. So remember, we're starting with 60 gallons. And then what are we adding and subtracting per unit of time? So we're adding 2 gallons per minute, and then we're subtracting or losing 3 gallons per minute times the number of minutes, T. So in the end, our expression for the volume as a function of time is 60 minus T gallons. All right, and so this makes sense. If T is representing minutes, since our rates are gallons per minute, then if T is exactly 1 hour, in other words, 60 minutes, our volume reaches 0. So that matches up with that piece of information. All right, so now that we have that, let's go ahead and set up part A. What I would like to do is set up my differential equation. So I'm going to scroll up a bit. Let me zoom out. Okay, there's that differential equation showing at the top of the screen. Let's set it up. My rate of change of the amount of solute per time is the rate in. I'm going to leave all of my units on here for a moment, but I'll drop them in a bit. 2 gallons per minute times the concentration in 1 pound per gallon, and then minus, I'm going to use this simplified version, the rate out, which is 3 gallons per minute, divided by the volume, which I have just written as 60 minus T gallons, and then times my X of T. That's what's unknown. All right. And so I wanted to leave those labels in for a moment. And of course, X is going to be in pounds so that we can see our gallons are canceling. So this bit of information is in pounds per minute. And then here, gallons are canceling. This is also in pounds per minute. And that makes sense to talk about the rate of change of the amount of solute. So the amount of solute is in pounds, and then we're talking about a rate of change with respect to time, so per minute. So I just wanted to point that out. I'm going to clear those out now. Okay, so now let's clean this up a bit and see what we have. We have x of t, or dx dt rather, is 2 minus 3 over 60 minus tx. And now what I'm going to do is I'm going to put it in standard form. So if you remember at the very top of the notes on page 1, we want the x prime and the x on the same side of the equation. So I'm just going to scoot that over, dx dt plus 3 over 60 minus t x equals 2. So you'll notice I kind of set that coefficient in front of the x off in parentheses just to kind of pull it to your attention because we're going to use that to find our integrating factor. So I'm going to write this as rho of t, not rho of x, because t is our independent variable. And this is going to be e to the integral of 3 over 60 minus t dt. All right, now, just note here that you may want to do a U substitution for that denominator to recognize that it's going to pop out a negative sign. So this is going to give me e to the negative 3 natural log of 60 minus t. Again, we're going to drop that plus c. I'm going to use logarithm rules so that I can simplify this. We have absolute value of 60 minus t to the negative 1/3. We can then cancel these. And what I get for my integrating factor is the absolute value of 60 minus t to the negative 3. Now, one thing that we had mentioned was that this tank is going to be completely empty after 1 hour. So I'm just going to make a quick note here that the tank is empty after t equals 60 minutes. And so what I'm going to note here is we'll just assume that t is always less than or equal to 60, so that 60 minus t is always greater than or equal to 0. So what I'm getting at here is I was very careful by including those absolute values, but in the context of this problem, I'm now going to drop them because I'm never going to be considering a t value that's greater than 60 minutes. So now I'm going to multiply through both sides by 60 minus t to the negative 3rd power. So I have my dx dt. Bringing that other 60 minus t up, we have a 360 minus t to the negative 4th x equals 2 times 60 minus t to the negative 3. All right, so we have multiplied both sides of this differential equation through by the integrating factor. And now what we would like to do is just double check that that left-hand side is in fact the derivative of a product. So if everything went correctly, it should be the derivative of the integrating factor times x of t. So let's just double check this. All right, what is that equal to via the product rule? So that would be, I'm going to do the chain rule, a negative 3, 60 minus t to the negative 4 times a negative 1. There's my chain rule times x of t. And then plus 60 minus t to the negative 3 times dx dt. And so sure enough, that does match up with what I had right here in green. So this is good. So now I can say that the left-hand side is the derivative of this product. And of course, the right-hand side, I'm going to leave some spaces. The right-hand side is 2 times 60 minus t to the negative 3. So what I'm going to do is I'm going to now slip derivatives with respect to t on both sides. Here again, the fundamental theorem of calculus just cancels out that integral and derivative, leaving us with the 60 minus t to the negative third times x of t. And on the right-hand side, again, if you want to do a u substitution, you can. It's going to kick out a negative. And so what we'll get here is a negative 2, 60 minus t to the negative 2 divided by negative 2 plus c. So in the end here, we are left with a 60 minus 2 to the negative 2 plus c. Now let's go ahead and solve for x of t. We have x of t equals, I'm going to multiply both sides by 60 minus t to the third or cubed. That leaves me with 60 minus t plus c times 60 minus t cubed. And we're not quite out of the woods, but we're almost there. Remember, I'm going to scroll up here for a moment. We had this sneaky initial condition where it said that the tank initially contained pure water. So that means that there was no salt in the tank to begin with. So our amount of solute was 0 at time t equals 0. So I'm going to say that x of 0 equals 0, which would make this 60 plus c times 60 cubed. So what do I have here? I have negative 60 equals c times 60 cubed, or c equals 1 over 60 squared. Negative, or negative 1 over 3600. So kind of an ugly looking C value, but a C value nonetheless. And so we can now answer part A, that the amount of solute at any given time t is 60 minus t minus 60 minus t cubed divided by 3600. All right. So here is x of t. That was part A. Let's scroll back up just to read what we were looking for in part B. What is the maximum amount of salt ever in the tank? So if you think back to your time in Calc 1 and beyond, whenever we talked about finding maximum and minimum values, we noted that those always occurred at the peaks of mountaintops or at the bottom of valleys, and that occurs when the slope of the tangent line is 0. So to find those maximum and minimum values, we always took the derivative and set it equal to 0. So we're going to do the exact same thing, but things are a little bit different in differential equations in that we're already working with the derivative. So first, let's just kind of jot down our thoughts. So to maximize, we want to set dx dt equal to 0 and solve for t. And so what I'm going to do is I'm going to go back up to the derivative that I started with. So let's look. I'm going to get a different color here. let's look right here. And what's interesting now is that I now know what x of t equals. So if I copy this down below, I have dx dt equals 2 minus 3 over 60 minus t times x of t. And so if I want, I could plug in x of t here. And then I'm going to, first of all, distribute this 60 minus t on bottom. So that makes this 1, and this brings it to a 2. And then I can also distribute this 3. So what I get here is 2 minus 3 plus 60 minus t squared over, if I take 3 out of the bottom, I'm left with 1200. All right, so that simplifies things a bit. And then again, what's my goal here? My goal is to set the derivative equal to 0. So I'm going to set this equal to 0. All right, now these constants here would be a -1. So if I move it over to the other side, I have 1 equals 60 minus t squared over 30, nope, over 1200. So 1200 equals 60 minus t squared. I am going to square root both sides. For now, I'm going to keep the plus or minus, and we'll see which one makes sense. So I have plus or minus the square root of 1200, which what would that be? If I take out 100, that'd be plus or minus 10 square root 12, which is plus or minus, I could pull out a 4, so 20 square root 3 equals 60 minus t. So t equals 60 plus or minus 20 square root, oops, square root of 3. All right, now only one of these makes sense. So at this point, if you plug this into your calculator, we do know that the positive one isn't going to make sense because that's going to mean that t is greater than 60, and there's no way that we could obtain a maximum in the tank at that point because the tank would be empty. So I'm just going to make a note here that t must be less than or equal to 60. So we know that t must equal 60 minus 20 root 3. If you want, you could get an approximate value out here, which I have as 25.36, or you could leave it as an exact value. And then lastly, plug that value into your x of t function. So again, either use this decimal or use 60 minus 20 root 3. And this comes out to roughly 23.09 pounds. So this is the maximum amount of solute, or in this case, salt, that ever occurs in the tank, and that occurs specifically at about 25.5 minutes into this mixture problem. All right, this concludes our notes over linear first order differential equations. And we will continue in the next section talking about substitution methods as well as exact solutions.